All right, so we're not missing anybody else at this point, no? Okay, perfect. So we can get started. So, right. So welcome to the second lecture. So this lecture will build a lot on what you have just seen about the standard model explained marvelously by Stefan. We're going to go a bit farther at the level of QFT. So again, I don't know exactly what your background is. I'm going to start asking you if any of you has ever heard of this SMEFT acronym before. Have you ever seen him, heard of it? I guess. Okay. So I'm going to explain no matter what, of course, but at least it gives me a sense of, okay, how are you doing? You haven't done so a lot yet, but please ask questions. Feel free to interrupt me. I think that this lecture is much better if it's interactive than if it's just me writing things at the blackboard. So I'm going to start by, I'm going to use a mix of Blackboard and slides. Okay, so the slide is going to be just there. I hope this works for everyone. I'm going to start by giving you an outline of the plan of the lectures for the 4 days. So we will finish on Thursday. And this is what I hope to cover. I'm not really sure about the timing, how far we will get into this program. Maybe we'll get too far, I don't know. So we will start today with a general introduction about effective field theories in general. And then we will look at this SMEFT, which, as you can probably guess, stands for Standard Model Effective Field Theory. And I will give you some generalities, and then we will start discussing this SMEFT in one particular setup, which is the leading order. So it's called the dimension 6 for reasons that I will explain you in a few minutes. So the course is called Predictions in SMEFT. So we'll talk about predictions quite a lot. So there is a part here. Where is that? Oh, no. There is a long part that we will do most likely tomorrow about doing calculations with this Lagrangian at tree level, a leading order. So there's a bunch of formalities that need to be defined. We will do some example. We will discuss how these are automated. So one of the lectures, I don't know if tomorrow or Wednesday, will be more about the automation, so state of the art of what people actually do to calculate these predictions. And then we will finish, if we have time, with a discussion of higher order. So what happens if one wants to go beyond this dimension 6 and beyond the tree level. Okay, so this is roughly the plan. This is a list of references that are, some of them are quite classic, so there are a couple of reviews. I will draw heavily from this paper here for the phenological part, but you can also check, so the lectures of Juan Rojo, they're really good for the pheno side, and there are some classic also references about effective field theories. I will try to give you material one way or another, so I will make sure that you have the slides, and I also have a couple of files with some useful formulas and even more references if you really want to dig a bit deeper into this, that I will upload somewhere, so I will make sure that they get to you. Okay, so I'm gonna leave that there, and I'm gonna start with the Blackboard part, really. So I want to start from, maybe this is more useful. I want to start from a general overview about effective field theory. So you have all taken QFT, I really hope. You have seen the standard model, which is a particular QFT that I have for electroweak interactions. So in general, you can always define what is called effective field theories, which are meant to be not complete field theories, but field theories that are valid whenever you have some expansion that we're gonna call delta in general. And this can be many things. So there are many effective field theories that can be constructed, and the generic feature, so the very general idea is that they approximate some more fundamental field theory in some limit. And you have this parameter that has to be some quantity much smaller than 1. So there are cases where this parameter is a ratio of mass scales, which is the one that we care about. There are cases where this delta is something even funnier. So for instance, you might have heard of soft collinear effective theory. And this delta there is something that is related to, well, it's an even non-relativistic object that is related to how collimated hadrons are. It's a very sophisticated thing, but it can also be something like that. So it can be a kinematic limit that we take, or it can be a ratio of scales that we care about for some reason. There can even be multiple deltas. So in general, whenever you have a theory, it can be arbitrarily complicated. You can have multiple expansions that concur at the same time. And the point is that because you have an expansion parameter, in general, an EFT is always some Taylor or Laurent series. So the fundamental idea under an EFT is that you define what your small parameter is, and then you calculate order by order in delta. So whatever your physics problem is, this gives you a breakdown of the relevance of the effects. So for the particular case of the standard model EFT that we care about, now this delta is a ratio of scales. So I can tell you that this delta, very roughly, it's the electroweak scale squared, really. Well, the electroweak scaled over some lambda, where this lambda is some sort of new physics scale. And this V is the electroweak vacuum that Stefan just told you about. So the V is the V that gives the mass to all the particles in the standard model. So it's the only dimension-full parameter in the standard model in the electroweak theory that we have. While lambda is some scale, roughly the order of the mass of the heavy particles, but more in general, it could be, I mean, if you have a strong interacting theory, this lambda could be the equivalent of lambda QCD for your new theory or something like this. So the standard model EFT is a theory specifically that is meant to approximate the effects of some new physics theory in the limit where this quantity is small, which means in the limit where you have some scale lambda that is much larger than the electroweak scale. So it means that you are specifically assuming that you have some new physics that is very far away from we are observing. What does this mean? The number, no one knows. So it could be a few TeV, it could be 10 TeV, it could be 100 TeV. The thing is, the physics is going to go like this ratio, so we don't want it to be too small, right? But so the assumption holds as long as this is reasonably, let's say, smaller than 1. So the whole idea of SMEFT is very related to something that is quite fundamental, which is this idea of the decoupling of physics. So there is something that is called a decoupling theorem. That was formulated originally by Appelquist and Carazzona. In the 70s, exactly 75. And I'm not going to do mathematics here. I'm not going to do the text of the theorem and the proof. I just want to give you a sense of what this is, because this is kind of the fundamental physics principle on which you base the construction of EVFT. So in order to be able to construct it, you really need to ensure that certain properties of the field theory are satisfied. So the idea here is very simple, and we're going to do it like this. So imagine that you have a theory, very approximate, like very schematic, where you have some field, ooh, I thought it was going to be better. Some field that is heavy. I hope you see that this is the red one. Man. Do you even see the color? I don't know, but okay. And some field that we have this line that is light. So forget for a moment about electroweak, standard model, and everything. So you just have something that has a heavy mass and something that has a light mass, and there needs to be some large hierarchy between the two. So what happens is that, the decoupling theorem talks to you about what happens to the one particle irreducible functions, so it's a statement about those technically, so we can think of it in terms of diagrams essentially, but technically it's a statement about 1PI irreducible graphs. So what happens is that if we decide to do experiments at the scale which is close to the light mass, but it's much smaller than the heavy mass, so there are a few things. So it happens that at this energy, we cannot produce the heavy particles on shell, so we just don't have enough energy in order to produce the heavy guy as an asymptotic state. It just doesn't propagate. So what happens is that these particles will only contribute as internal lines of a graph. My God. Okay. So the heavy is only an internal line. So it means that, so the external states are always going to be light only, so we don't need to have them as asymptotic states in our theory. Another thing that happens is that because we don't have enough energy to produce these states, they will always be off shell. So here in a diagram like this, you're assuming that S is much smaller than the heavy mass that is in there. So basically, you never hit the pole of the resonance, which means that at this energy, the diagram is going to be completely analytical. If you remember from some QFT course, the scattering amplitudes have non-analyticities that are associated to the pole, so you have infinities that are hit there to some extent. Because here you never hit them, everything is completely analytic. There is no pole or nothing funny like that. The other thing that happens is that, so this guy in here had some propagator, right? So this was something like S minus m squared. It could be a vector, it could be a scalar, it could be a fermion, it doesn't matter. It will always have a pole that has something of this form. So because we are approximating at S that is much smaller than m, we can do the Taylor series, and you would say that this will go like minus 1 over m squared, and then you will have some corrections, right? So you have these plus higher powers of S over m squared. So what you're seeing here is that you are essentially going into a kinematic limit where your delta is your S over m squared. So it's the energy at which you are working suppressed by the mass of the particle that exists but you're not producing. And so putting together these elements, what the theorem tells you is that a diagram like this can be equivalently described by a contact point. So you can have a theory where you can have only a contact vertex between the 4 light particles. And this interaction will be an interaction that is analytic all the time. It is local, and it has to scale with some inverse power of the mass. So we thought of this for a specific diagram looking at it, but the point of the theorem is that this generalizes. So you can have, let's see, you can see both. So you can have any sort of graph, and this will always be true. You can even have it at loop level, for instance. So if you have something that had light stuff here, and then you were exchanging 2 heavy particles in a loop, then this will be equivalent to a sort of diagram like this, where you have 2 effective interactions like that. So the point of the decoupling theorem is that if we go to energies that are much smaller than the mass of a certain particle, then the theory is equivalent to an EFT where, so the only dynamical degrees of freedom are the light particles, and it contains, so, and the effect of the heavy states is encoded in local analytic interactions that are suppressed by some powers of the heavy mass. So the statement is made in general. So in the original theorem, it was made for fermions and mesons, but it's something that really generalizes to any theory. So you have something heavy, something light. What happens is that if you go to energy where you can only see the light, basically you can forget about the heavy degrees of freedom, and you can construct a theory knowing only what your light particles are, but then you have to ensure that there are these sort of interactions that can encode the impact of heavier particles, and they have to be local analytic, so these behave like usual vertices, but they have to scale like the inverse powers of some heavy mass, which kind of goes in this direction. No? So like you will have some suppression of the scale of new physics. Now, I should give you some caveats in the sense that this theorem, if you state it properly and you prove it properly, it has assumptions. So it's not always guaranteed the new physics decouples. It needs to have some characteristics. In some cases, it doesn't decouple. There are cases where it doesn't. For instance, if you have a particle that is part of a multiplet and you decide that the heavy one is only one member of the multiplet, but not the other, so you're kind of breaking the symmetry in doing this. In that case, you will have some effects that remain finite and do not obey this kind of relation. Or you can have it if you have some sort of strong decouple, strong interaction effects that change essentially the way that the fields behave. So think when you go from quarks to mesons, that's not the same field, so it's not obvious that you can decouple in this way. Or if there are special relations between decoupling. So one famous example of non-decoupling physics, you might have seen it without knowing it, is the top quark. So if you have gluon fusion, okay, where you have the two gluons with the top that runs in a loop, and then you produce the Higgs bosons. You might have seen this because it's the #1 production mode of the Higgs at the LHC. You have a top that runs in the loop there, right? So typically, people do this calculation, reducing this down to an effective vertex. And this is valid whenever, so essentially the momenta are smaller than the top quark mass. So this approximation is actually quite good for PTs of the Higgs up to 300 GeV or something. So if you have low momenta that are ingoing in the external particles, then this is actually a good approximation. But if you calculate this loop, it will come out. So this has an expression which is roughly this. So it is an alpha half for pi, and then there is a loop function, and if you expand the loop function in this quantity, it will start with a constant plus 7/90 of, well, this is not even the momentum, I think it's the mass of the Higgs squared over 4mt squared, and then you go on, and you close the bracket, sorry. So it doesn't really matter what comes after, but the point is, if you take this and you expand it in the limit of the large top mass, you have a constant. So it means that even if mt goes to infinity, these loops survive. So this doesn't obey the law that this has to go like 1/m top squared. Why? Because here there is a Yukawa, and the Yukawa is proportional to the mass. So the two are canceling in the ratio. So you are assuming that the mass is very heavy, but you cannot send the Yukawa coupling to infinity, otherwise you wouldn't have this loop. So you are saying, I want to keep the Yukawa finite, but send the top mass to infinity, so you are breaking somehow the gauge invariance of this object. And so this particle essentially doesn't decouple, so there is a finite effect even if you send the mass to infinity, if you want to keep the Yukawa coupling. Okay, so this is a famous effect. So if you hear, yeah, but the coupling theorem has limitations, yes, of course it does. But then, so there are also other signals here that tell you that you're doing something strange, right? So if you wanted to construct this from the bottom up, you would know that you need, so essentially that you're missing a particle because you need to complete also the SO2 multiplet with the bottom quark and so on. All right, so this idea here is very general and it's very powerful, so now forget about the exception. I'm gonna erase this. So the decoupling theorem can be very reasonably assumed to work for new physics. And the very powerful idea that is underlying it is essentially the basic idea of separation of scale. So it looks a bit sophisticated because I did it for a QFT. But essentially what this is saying is that if you have something that is very heavy and is really like with a mass that goes to infinity, then its physical effect, because it goes like 1 over m to some power, eventually goes to 0. So this means that even if you have particles with masses at the Planck scale or masses at the GATT scale, you are not supposed to see their effect yet because they are suppressed by 1 over m to the n. It's the same principle that applies also to the fact that, so if you want to do nuclear physics, you don't necessarily need to know the electroweak theory or to do QCD. If you want to do chemistry, you don't need to calculate with the standard model. So it's the principle of essentially each theory is valid at a certain energy range, and then at a higher energy range, there is something else that is valid, but you don't need to know the full theory of everything in order to be able to calculate in a lower energy setup, because the effects of something that is very heavy or that exists at very high energies is gonna decouple, so you're not going to see it. It's trivially the same concept of if you see an object from very, very far away, it looks like a dot, because it's in the first approximation, let's say the shape that you can see is the classic spherical cow. Like you look at it from far away, you don't really see the shape. If you get closer, then you are at a distance where you can resolve more details, but the details decouple from the physics that you are doing if you are very far away. Okay, so in the end of all this story, what happens for the specific case of the field theory is that, so you construct a Lagrangian that we said contains only the light degrees of freedom. And we'll have these interactions that go like 1 over m squared. And these interactions will be of a form of a C that in general depends on a scale, and then an operator that in general depends on the scale. And this is usually called Wilson coefficient. And it is dimensionful, so this C has to be some dimension that is smaller than 0, so in the sense that typically if you want to have interactions that are suppressed by 1 over m squared, these will have dimension -2, so it goes like in a 1 over m squared, and so on. And this is usually called the operator, which is just an interaction term. So it's an interaction term like every one that you write in the Lagrangian, but to distinguish it from the usual terms. So the EFT-specific language is to call it operator. So operator in Wilson coefficient. And what you're doing here is that you're essentially taking that principle, and the Wilson coefficient will be the coupling that enters into this interaction, right? So the Wilson coefficient is the object that contains all the high energy physics, so the high energy things that happen. So what kind of particle was this exactly? What kind of couplings did it have? Did it respect parity or not? So this falls all into the structure of the Wilson coefficient. The value that this guy takes depends only on the high energy factor. While the operator is the part of the interaction, so it's the external fields that I'm attaching to the vertex. So this is essentially the light physics. So you are kind of doing this decoupling of this is the heavy and this is the light part. it's a factorization, let's say, into UV and light components, which again, conceptually is something that is not too far away from what you do when you do PDFs, for instance. No? So when you do PDFs, you want to calculate some cross-section, and you do, okay, I do the integration of my Parton level cross-section, which is the hard interaction point, and then I have some structure functions, and I integrate in S or in Q squared, whatever, so X, technically, you're integrating in X. So this depends on X, and this depends on X. So if you have that this is the PDF, and this is the hard scattering, this is exactly the same concept, right? So the hard scattering is like the Wilson coefficient because it's the high energy part of the collision that you're doing. And this is kind of the low energy part, so it's telling you how you source the low energy so interaction of the interactions. So it's really always the same principle that comes about. So it's a principle of separation of scales and of factorization of the physics that you can do. Okay, so going to a bit more technical side, an EFT in general is defined by two things, or three, depending on how you count them. So what you need to specify to construct an EFT is first the field. And second, the power counting. So the power counting is basically who is your delta, okay? So the idea here is that what we're trying to do is that we're trying to kind of reverse this reasoning. So that the way that the coupling theorem is formulated is that you start with a theory where you know that you have something heavy, you know that you have something light, and you do this operation of going to the limit of E much smaller than M. So this is kind of the top-down approach because you know what comes up and then you take the limit after. But the true power of this thing is that you can reverse it. So because this theorem holds, you know that you can always take a theory where you define only the light degrees of freedom. So who are your light degrees of freedom that are running into your theory? What kind of symmetries do they have? What rules do they need to respect? And then you can make them interact with these interactions that are suppressed by 1 over m, and then construct the EFT from the bottom up. So you can just say, okay, what is everything that I can possibly write down? And this, by definition, will have to capture the effect of something that was heavy. The thing that you don't know is what is the value of the Wilson coefficient. So when you do this from the top down, you will calculate exactly what this Wilson coefficient is because it encodes all this heavy physics. While when you do it from the bottom up, you just leave it as a free parameter. You can do that, and you will make sure that you capture everything, right? Because if you have something heavy, it has to fall into that box. So if you write down all possible interactions that you could have, you must be capturing everything, right? So the power counting is essentially the rule that tells you, okay, how do you classify all this, everything that you can write down in order? So this has to be a series, has to be calculable order by order in some parameter. So what is your parameter? And for SMEFT, we already said before, that this was going to be V over lambda. So technically, we're going to count in canonical dimension of the operators. Which is just the statement that if I have an object that is of canonical dimension 6 as an operator, then the coefficient that comes in front will have to have a lambda squared at the denominator to match up the dimensions. So this will be order 1 over lambda squared. If I have something that is dimension 8, it will need to have 1 over lambda to the 4th. So this is another order in the parameters, and this is how we will organize the whole series. I will go back to this again. And the degrees of freedom are really the choice of who are your dynamical fields. So if we want to work in SMEFT, we are assuming that we live at the electroweak scale, and we give the standard model for granted because we have been producing all the particles in the standard model from up until the Higgs and the top. We can definitely produce them at the LHC, for instance. So we can say that all our light degrees of freedom are the fields of the standard model. One is example that is actually convenient to do at this point, and it's also very nice because it matches very well the introduction that you had before from Stefan, is the example of the Fermi theory. So I think this is an example that is very explicative and kind of summarizes quite well all the concepts that we have discussed so far. Okay, so the Fermi theory was used for decays, right? So you can use it for, well, originally it was introduced for nuclear decays. So you had, where did I leave this? Is this the piece of paper? Yes. So you had this interaction that you have seen just in the previous lecture, where you had, for instance, a neutron that can go to a proton. And then you emit, this has to be negative, so a neutrino, an antineutrino, and an electron. You can have exactly the same graph for something much easier, which is you have a muon that goes to, here it's a neutrino, and then again, right? So it's exactly the same shape of the decay. So this thing was introduced in the 1930s, as you have just seen. So it's a theory that holds for energies that are comparable to the mass of the neutron, which is 1 GeV. In this case, it's even worse because this is energies that are order of the mass of the muon, which is what, 100 MeV. I hope I'm not saying something stupid, sorry, but it's much smaller. So if you are at this order, we know today that what is actually causing that is that you have a W boson, you have just seen it before, that is exchanged in here. So actually inside here it is exchanged by the quarks, but okay, it's still a fermion, you can think of that that way. So you have a W that is exchanged in the middle, and the mass of the W is 80 GeV, right? So at this point you have that energy over mass of the W is 1/80. And there's more than that. In that amplitude, it comes in squared because we know that the propagator has 1/q squared minus mw squared, right? So if you square this is suppressed by the order of 10 to the 4. So this is your small expansion parameter. So for this particular theory, you have that your fields and symmetries are so either the light fermions of the standard model, so for the fields, so the muon, so the light leptons and the neutrinos, or you can even have the composite states because you're at an energy where you're technically below lambda QCD, right? So you have already formed the neutrons and the protons, and you do have the electron and the neutrino because they are definitely lighter than 1 GeV, so they can exist. The symmetry is QED, so this just has to respect electric charge. That's it. It can do everything else. And then your power counting, so your counting, well, technically is still the canonical dimension, but then in practice it comes out to be this E over the mass of the W. So this is your small quantity that you are expanding in. Right, yes. And so the idea is that, so to revise the reasoning, so we know today that this is the full theory, so we know how to apply the decoupling theorem. This guy decouples. So if we take the limit, it can be squeezed down to an effective point, and so on. We know it's an effective point interaction. This is a dimension 6 interaction because you have 4 fermions. So it has all the problems that Stefan just explained, so this cannot be the full theory, but it is definitely a good approximation to this when you are in that limit. But we could have done also the bottom-up version. So it was always possible to write down this object without knowing that W existed. This was done in the 30s the W was hypothesized in the 60s, it was discovered in the 80s, okay? So the principle is really of, I don't know, so this is clearly not a full theory, but I can definitely write this down. So I do it, I can calculate with it. You could do loops, you can do anything you want with this kind of interaction. It is a properly defined QF theory, QFT, let's say, order by order in the expansion parameter. You know that it's not the full theory because it is not renormalizable, and we will come back to that in a minute. But nothing prevents you from writing it down and using it to calculate. There is even more that you can do. So you can start considering, for instance, I don't know why, okay, where are my notes, but okay. You can start considering all the aspects that you have just seen this morning. So there is a coupling constant here that is called G Fermi for historical reasons. So this is the Wilson coefficient of the theory. And it has dimension -2, because it's a dimension 6 interaction. So G Fermi has inverse dimensions of a mass squared. You could have called this GF prime. There's no reason why the two coupling constants have to be the same, right? No, they are completely different particles. But you can go and measure. You can measure the decay rate of the neutron, you can measure the decay rate of the muon, and you can measure this Wilson coefficient. And it turns out that they're actually the same. Why? Because the electroweak interactions are universal. So the W couples exactly with the same coupling to the quarks and to the leptons. It doesn't distinguish. And this is a feature of the standard model. It's not a feature of the physics that we're seeing there. You could have done more. You could have seen that there's some violation of parity. We have just seen that, right? So the experiment of parity violation were done already, I think, in the 50s. You could have seen that there is some flavor conservation. Well, okay, this is hard to see because you didn't know how to measure the flavor of the neutrino, but it does do that. There is definitely conservation of the lepton number. Yeah, so you could have collected, I'm thinking if there's more, but you could have collected a lot of hints. Specifically, the measurement of G Fermi, if you write it down as a number, it turns out to be roughly 1/2 nanti GV squared. If you just invert it, so it's 1.11 something, and if you just invert it, take the square root, you get 290, which is not the mass of the W, but it's relatively close to the electroweak scale, which is 246. So if you wanted to discover the particle that was causing this, you knew there was something more, and they had to be there. And so what kind of particle is inside this dot? You just inverted this number, you got 290 GeV, you would have said, yeah, okay, that is the target. We need to construct a collider to go in that direction that can sample energies of this scale. Then, okay, it was enough to get to 280, so it's away by a factor of 2, so you didn't need the LHC to discover the W, but still, I mean, up to a factor of 2 is a very good estimate of the energy scale of the physics that is living inside the dot. So this is all kind of showcasing the power of DFT. Then, of course, history takes many routes. So there has been this hypothesis of putting the boson explicitly in the middle, so you could calculate also assuming that there was a boson in there. You could be a bit more precise, do all the studies that are needed to actually discover it. But if you just wanted a rough estimate of where the W was going to be, you could have gotten it in the 30s. Okay, with no idea whatsoever that the electroweak interactions were there. So this is a bit the idea of why effective field theories are popular now, because we have no idea what else is there. And so this could be an interesting method to get some hints about which way we have to go, what is the energy target for the next collider to actually discover something. So we had some ideas, but LHC didn't find many things, let's say, around the TeV scale. So it's possible that, it's actually consistent with current data, the new physics is not in the multi-TeV window, so it's like something from 3 or 5 TeV and higher, right? Just because we haven't discovered anything yet, so we know that there is very little in that window. There could still be something hiding that is very poorly interacting. We have not excluded it completely, but it could be that something is just heavier, and so one can use this kind of strategy applied to the standard model this time try to measure the new Wilson coefficients that we have, and then see to what they quantize to. So they can give us indications about the scale just by identifying their value. They can give us all other sorts of indications about how symmetries play around. No? So the equivalent of, oh, this has to violate parity, it has to violate flavor, it has to violate something else, or it has to preserve it. And then we can use these hints in order to guess which BSM model could be more realistic than others. Okay, I just want you to, before taking a break, tell you a couple more things, but I don't know where I left my piece of it. Ah, it's this one. Okay, perfect. Okay, so let me just write down SMEFT before we break, because at least we've gotten to a decent point. Eraser here. Okay, so putting together the things that we have said, so we want to apply this reasoning to the standard model. This is the thing that is interesting right now. So we want our light degrees of freedom to be those of the standard model, so all the SU2 doublets, triplets, and things that you have just seen. We want the symmetries to be those in the standard model. So specifically, For the symmetries, there is already some caveat. So for symmetries, we definitely want the SU3 cross SU2 cross U1. Because this is the gauge symmetry. So remember, this is the only thing that is super duper sacred about our knowledge. You can do everything, but you can never, ever break this. Okay? Then it turns out that the standard model, if you look at it, you've seen it already in the lecture before a little bit, it has a few more symmetries, actually, which are accidental. So you just write it down, and it turns out that this remains roughly symmetric under something. And it's the baryon number. And then you also have the 3 lepton numbers if you neglect neutrino masses. So the E, the mu, and the tau. So if you neglect neutrino masses, you preserve the lepton numbers in the individual flavors, and you also preserve the baryon number. These are accidental. So when you go to the standard model, so the SMEFT, so you extend the Lagrangian of the standard model, you can decide if you want to retain this or not. And the power counting, we just said it's in dimensions. So the Lagrangian of the SMEFT is going to be made by a Lagrangian in dimension 4, which is exactly the same as the standard model Lagrangian. Then we will have a dimension 5, a dimension 6, a dimension 7, a dimension 8, and then we go on and on and on. So these represent the orders of our EFT. Okay, so a leading order, you have the standard model, which makes sense. And then you have other orders that get smaller and smaller and smaller. And for each of these d-dimensional Lagrangians, basically you will have some sum over something with a label. It can be convenient to write it like this. So you have some Wilson coefficient, some operator of dimension d, and it will be suppressed by d minus 4 powers of lambda. I hope you can read it and that this makes sense to you. So if you are at dimension 4, you don't have any new physics scale suppression, you just have your interactions. If you are at dimension 5, you will have 1 over lambda, dimension 6, lambda squared, and so on and so forth. Obviously, this is because the Lagrangian needs to be dimension 4 in order to have, so you have to integrate it over a 4-dimensional space-time, so that's why. So at each of these level, you will have some free parameters. Well, those of the standard model, they are already determined, so they're not free anymore, and they have historical names. But those that come after, they are free parameters that are the thing that you want to measure, and they accompany these interactions. The interactions are made just by standard model fields, but they have higher dimension. So at dimension 5, just let me say this to conclude it. Dimension 5 is peculiar. Actually, all the odd dimensions have this nice feature that at odd dimensions, just because of a question of combinatorics with the fields that you have at hand, so you need to use the standard model fields. So if you want to have an odd dimension, you sort of have to use the fermions. So at odd dimensions, you can prove, and there's a paper proving it, that you always need to violate the barrier number and or the lepton number conservation. So if you are at dimension 5, there is only one guy that you can write down. So it will have some C over lambda. And it has this structure, so it has a Higgs doublet tilde, a lepton, and then here you will need to have a lepton charge conjugate and the X tilde star. So you see it is a bit funky. So the charge conjugate of a field is always the charge conjugation matrix, which is the 1, gamma 2, gamma 0, yes, and transpose and bar transpose. So this is the thing. It violates the lepton number clearly, so you can only write it down with leptons. Why? Because the lepton doublet has exactly the same hypercharge as the Higgs doublet up to a sign. So the tilde fixes the sign such that H tilde L has a vanishing hypercharge. You cannot do this with the quark because the quarks have 1/6, not 1/2. So we'll never find a combination with only two things that is invariant under the hypercharge. And this is what you need to do in order to fix up the sp2 indices. So it is written in a complicated way. What it does is that it creates Majorana masters for neutrinos. So this is called the Weinberg operator sometimes. So if you open it up, so you do the exercise of doing that the Higgs takes a VEV. So the doublet becomes a V plus H over square root of 2. You go to unitary gauge. You forget about the Goldstone bosons and so on. These will give you out something that is, so a left-handed neutrino like that, and you will have a V squared in front and a C and a lambda. So this is kind of as dimensions of a mass, so a V squared over lambda. And this is the Majorana mass term for neutrinos that you get, for instance, in the seesaw models. So from the point of view of DFT, it's a statement of symmetry. So if you decide that your SMEFT has to preserve the lepton number, then you are automatically saying that neutrinos have to be Dirac particles. Or if you allow the lepton numbers, which by the way was just accidental, to be violated because you can write it, well then they are automatically Majorana particles from that point of view. And then there will be some UV completion that produces this potentially. Okay, so all the odd dimensions violate B, N, or L. So the thing that is mostly used for phenomenology is dimension 6 for the bare reason that it is the first level at which you need, so at which you get some corrections to standard model interactions that do not violate the baryon lepton number, right? So just sort of standard vanilla corrections to the phenomenology. You might wonder at this point, yeah, but okay, if this is a series in lambda, and at dimension 5 I have the neutrino masses, this is already 10 to the minus many numbers. At dimension 6, this is going to be even smaller. Not necessarily, because so what happens here is that we are calling everything lambda. So lambda is kind of a placeholder for something that is dimensionful. We'll just write lambda for everything, but really, when one goes and tries to connect to some new physics models, there can be many lambdas. So you can have a scale of new physics that is associated to the violation of lepton number, for instance, the mass of the right-handed neutrinos in the seesaw model, which has nothing to do with some other physics scale that is associated to new physics that instead preserves the lepton baryon number. For instance, if you have Z prime, if you have SUSY, if you have anything else, this doesn't give you this operator, but it does give you dimension 6. So in principle, you can have different suppression. So the fact that this is super tiny doesn't imply that the rest of the tower is also super tiny, at least the even dimensions. Okay, so I think this is a good place to stop for 5 minutes, and then we can start again. Can we start again? 5 minutes are very short. Okay, so before starting to calculate with the SMEFT, there is one last part that I want to cover. which has to do with renormalization. Now, don't be scared, I'm not actually going to do renormalization, so you're going to see it probably in the other courses, like fundamentally. The only thing that you need to know is that renormalization has to do with reabsorbing divergences inside some counter terms, okay? So you need to have enough counter terms in order to be able to absorb all the divergences that you have in the theory. This is what defines a renormalizable theory. And you heard already before that it came up in the case of the Fermi interactions, but really it's a problem of all the EFTs. They are not classically renormalizable. So I want to explain a bit more about what is meant exactly and why we can still do phenomenology with the SMEFT. So the second one has an answer that is very short, which is these EFTs are not renormalizable in the classical sense, so they have an infinite number of infinities in the theory. But because they are EFTs, everything in EFTs lives order by order in your power counting parameters. And it turns out that you can renormalize the theory order by order. So it means that you have infinite divergences, but you have a finite number at dimension 6, a finite number at dimension 8, a finite number at dimension 10. So if every time you truncate the theory to a finite order, you are by definition neglecting all the infinities that come up at higher dimensions. And so you remain with a finite number that is always sufficient to be reabsorbed. Still, I mean, this tells you that the theory can only be used up to finite order. So this is the characteristic of DFT. Like, you can work with it, but it has to be truncated all the time because it's always approximating something else. It will never be the ultimate theory of nature. This is one of the elements that essentially tell you this statement, okay? So I want to give you a quick recap of how we determine if a theory is renormalizable or not. So it's always the case that some interaction term that has dimension larger than 4 basically leads to a non-renormalizable theory. This you might have seen in the QFT courses, it's in the Peskin and all these kind of books. So we can revise that. And then I hope to convince you that this SMEFT is renormalizable order by order, and this is what is actually done in practice to calculate. So we will stick to one loop for concreteness. So when you have one loop, what happens is that you always end up calculating some integral with some loop momentum, and the loop momentum enters in a diagram with some power that we're going to call d minus 1, and d is the superficial degree of divergence. Of a diagram. Okay, so you take your theory, any theory, you calculate one loop diagram, and in the loop you will have to do this integral. And the momentum that runs in the loop will come with a specific power, and this depends on the diagram that you have. So the diagram can be divergent, convergent, or so on. So if your d is larger than 0, then this is really divergent. If your d is exactly equal to 0, this is logarithmically divergent. And if it's smaller than 0, then it is convergent. Just by complex analysis considerations. Now, the trick is that you can do some combinatorics on which you can trust me. I can give you the final formula. Then if you want, you can play with it and convince yourself that this is right. So you can always, there are many ways you can write this, so I hope this makes sense. So you can calculate this degree of divergence as with this formula. So this is a 4 plus a sum over, I'm going to call this index I. So I'm going to put in a lot of symbols, and then I'm going to tell you what they are. And then there's a minus, a sum over F, so, and an MF. And this, the I, is some delta I plus, again, the sum over F of some small n IF. Sorry, there's a lot of things and indices, but now it will become clear. You don't need to understand this in full detail. Okay, so now, F is an index that runs over particle species. So fields, for instance. Then EF is the number of external particle of type F. MF is the canonical dimension of the particle F. So typically it is 1 for bosons and 3/2 for the fermions. I'm not going to do anything more sophisticated than that. While the index I, this label types of vertices. Now we're going to do an example so it becomes clearer, hopefully. And in each vertex, so then you will have an Ni, which is the number of vertices in the diagram that are of type I. And the little delta I is the number of derivatives or equivalently momentum powers that you have in the vertex I. And the little nif is the number of particles f in the vertex I. So if you do it like this, the way that you're calculating the superficial degree of divergence is that you have a 4. Then here you're summing, so this lowercase d essentially is the dimension of the interaction minus 4. So if you have an interaction term, everything that can give you a dimension in the interaction is the fields that it contains. So each of the fields that enter in the vertex have their own dimensions. So you have to sum the dimensions that come from the fields, and then you have to sum the dimensions that come from the derivatives. Okay, so this is the dimension of the interaction. If you're in the standard model, this is always smaller or equal 4. You subtract 4 because it's part of the combinatorics game. So you count basically how many dimensions enter into the diagram because of the vertex, and then you subtract the dimensions that come from the external lines. We can do an exercise to convince you, but this is, trust me, it works. So we can do a practical example so you see it. And then once you have figured what this is, it's very easy to say why a theories are normalizable or not. Okay, so imagine that you have, take the standard model, you might be familiar with this, or even just QAD. So you have some vector, and then you have basically the vacuum polarization diagram. So if you do it like this, so you have, I'm thinking where I should start from. So you have two vertices that are of this kind, right? So you have the vertex of the vector with the two fermions, and there are two of them because there are the two vertices that enter here. And the dimension that the vertex has, this is a standard model interaction, right? So it should be the dimension of the vertex minus 4, so this should be 0. But we can check it. So this does not contain any derivatives, so the delta is a 0. And then you have the sum over the dimensions of the fields that enter. So there are two fermions that do 2 times 3/2, and then there is one boson that has dimension 1. We subtract 4, and we should get a 0. Okay, so this part of the first term basically vanishes. And then the external fields, so the only fields that are external is the boson. So you have the number is 2, and the dimension that it has, each of them is 1. So if you put all of this together, you will have a 4 plus a 0 that comes from the vertices, and then you have to subtract 2. So this is 2, it's positive, so this guy beautifully diverges. And this is one of the first things that you see in field theory when you renormalize QAD, so this is divergent, okay. Now we can make another one here. Okay, so if you now have a box, in the same theory. So what we are changing now is that we have the same kind of vertices, but now we have 4 of them. Still doesn't matter because they still have dimension 0, each of them. They're all normalizable vertices. But now we have 4 external states, each of them with dimension 1. So the degree of divergence of this diagram is going to be 4 plus 0 minus 4. So 0, so this is a logarithmically divergent diagram. And finally, we can do something like this, like a sunrise with like attached vertices. So now we have 2 types of vertices. So there are vertices like the ones before, and we have 2 of them, but each of them have dimension 0. And then we have the triple gauge couplings. And we have 2 of the triple gauge couplings, but now they have, no, they still have dimension 4 because they are still standard model interactions. So the way that you calculate dimensionality of the triple gauge coupling is a bit different because they have 3 fields. So, okay, so I can do it. So these have one derivative that has to come in, if I'm not wrong. And then you need to have that it has 3 fields and minus 4 in the end. So instead of having 4 dimensions that come from the fields, so 3 and 1, you have only 3 dimensions that come from the field. But if you check the Feynman rule, there's a derivative always in here, because this is always some x mu nu, w mu, w nu, for instance. Yeah, and finally, we have 2 types of external states. So there is the squiggle, for which we have 2, and each of them has dimension 1. And then we have the fermions, and we also have 2 of them, but each of them has dimension 3/2. So if you put together everything, this is a 4. This still contributes with a 0 from this. And then from the external lines, we have 2 plus 3, so we have a minus 5. So this is minus 1, it's negative, and so this diagram converges. Okay, so this is how you're supposed to use this formula, which is, okay. It can be derived quite easily, so if you know how to calculate the diagram, you can just figure out how this goes and why it has to go this way. Now, the point that I want to make is the following, and I need to take another thing. So, so far we've been discussing, so we've been characterizing EFTs by the dimensionality of the interaction. So what we need to ask ourselves, so this is a formula that tells you when a diagram is divergent, depending on all the dimensionalities that are around. So if you have dimensionality, so the little d, that is dimension of the vertex minus 4, that is always negative. So it means that, well, it's actually smaller or equal 4. So it means that you have a Lagrangian which, well, that contains only interactions with up to dimension 4. Right? So you don't have any higher dimensional interactions with dimensions that come from fields and derivatives. Then you will have a classically renormalizable theory. So this is what happens in the standard model, for instance. And this is renormalizable because using the formula of the superficial degree of divergence, this will always need to be less than 4 minus the sum of the dimensions of the external fields, right? So because this is always a positive quantity, so you're always going to have some dimension fulfilled. So it means that this is always less or equal 4. And you can also check that there is only a finite number of cases where this is positive. So what happens here, so I'm trying to go step by step. So if you have an upper limit on the dimension of your interactions, so your degree of divergence is bounded by this formula, okay? So you know that you will have divergences where this number is greater than 0. This is telling you that it has to be smaller than 4, okay? So you have to worry about the cases where you can get a number that is between 0, equals 0 also because it's log divergent, and 4. So it means that you have to worry about the cases where this object is smaller or equal than 4 itself. Okay. And there is only a few cases. So if you know what kind of fields you have, for instance, if you want to have fermions, each of them will have dimension 3/2. So if you have 2 fermions that are external, this quantity in the brackets will already be 3. If you add the 2 more fermions, this is greater than 4, so it's already okay. So if you have fermions, the only case that can be problematic is if you have 2 external lines and potentially attaching another boson. This will make 4. If you have only bosons, you saturate these when you have 4 bosons. If you have more than those, then the diagram will be convergent and so on and so forth. So the point is, you should do the counting properly, so you can count here how many possible diagrams you can have at one loop, in this case, that create divergences. And if you have a theory that has only interactions that are at most dimension 4, then there is only a finite number. You can check that is equal or less than the 3 parameters that you have in the theory, such that you can define enough counter terms to eat them all up. Okay, so this happens. In the standard model, you can do it. In QED, you can do it, and so on and so forth. Now, if you go to an effective field theory, what happens is that in some cases, you will have a dimension that is larger than 0, okay? Because you will have, for instance, dimension 6 interactions will give you this di equal 2. So this di measures the XX compared to dimension 4. So if you have, for instance, dimension 6 SMEFT, then your inequality will be that this is 6 minus the number of external fields that you have. And this is always less or equal than 6. Now, so this is also finite, okay? So if you decide that you go only to dimension 6 and you truncate, you move a bit up the bar. So here you can have things with 4 fermions, like the Fermi interaction. So you can have one loop diagrams with 4 external fermions that diverge. But you can eat it up essentially because, so the only cases where you will have divergences is when this d is larger or equal than 0. So it is all cases where the sum of the dimensions of the external fields is at most 6. So this is literally telling you that, so this is the maximum dimension of the counter term, or of the operator that carries the counter term, let's say, that you need in order to reabsorb the divergence that you will have. So I'm explaining in a super confused way. I can try to make it a bit more explicit. So just by the combinatorics of the thing, so if you imagine that you have, so we said you could have some sort of diagram that is one loop, and it ends up having 4 external fermions, right? So this would be divergent because, so it can contain higher dimension operators, so there can be a 6 here, and then the sum of the external, so the sum of the dimension of the external lines is also 6. So this can have a d equals 0, essentially. So you can have some sort of log divergence. So if I have this divergence, what kind of counter term do I need to eat it up? Well, I need a counter term that acts like this, so that in the Lagrangian, I write it like z something, and then it will have the 4 fermion interactions that I need. So this z counter term will also have to come with a dimension 6 operator. And that formula there is telling me that if I go to one loop and I have dimension 6 operators around, I can never find a divergence that needs a dimension 8 counter term to be eaten up. So any divergence that I have that contains only up to dimension 6 operators, because it is divergent, so it has a limited number. So if this guy had more external fields and it went to a dimension 10 or 12 operators, then it would not be divergent if it only contains dimension 6 interactions. Okay, so the combinatorics is such that if I go to dimension 6, I can only have divergences in diagrams such that with the external lines, I get to at most dimension 6. If I go to dimension 7, it does the same with dimension 7, and dimension 8, and so on and so forth. So this is actually kind of a deeper statement, but it's easy to see in the combinatorial formula. I'm sorry if it's a bit confused, but if you think about it on your own for a second, you will realize that. So it's really telling you that at each dimension, you can always you can only need the counter terms in the same dimension to reabsorb the divergences. So order by order, the theories are normalizable. If I work to dimension 6, I will have the dimension 4 interactions that renormalize themselves, and the dimension 6 ones that renormalize themselves again. And then dimension 8, I add more, and I add counter terms, and so on and so on. And this is a feature of the power counting that we chose. So we chose specifically that we were going to order the SMEFT by dimensions. So what I call the first order is dimension 4, and then 6, and then 8, and then so on. But we didn't have to. So there are theories where the power counting is a bit more complicated, and then it does not really align with canonical dimensions, and those are a bit more problematic. So there are theories like chiral perturbation theory, for instance, where you deal like, you might have seen it for pions, so you put like the exponential field with the pions and so on. That is ordered in derivatives, and it's a little bit awkward. Basically, at each order, so if you have 2 derivatives, you produce divergences that have 4 derivatives, and then you are forced to introduce counterterms of the following order. At that point, you produce divergences that have 6 derivatives, and so you need counterterms of the following order. So the theory is still fine, but kind of the normalization always spills into the following order in the theory. While in SMEFT, this doesn't happen. SMEFT exactly closes because it shows exactly the canonical dimension as a power counting. So this is one of the biggest pluses of this theory that makes it easy because you can calculate loops and you can never worry about the next order, otherwise it would be really complicated. Okay. I hope this kind of makes sense. Okay. All right, so where was I? Okay, yes, so before starting to look into this more specifically, I want to give you a bit more of a big picture. So we talked about effective field theories in general. We talked a bit about the Fermi theory from the historical perspective, then we introduced SMEFT. And we kind of said already that the idea is that we would like to use this SMEFT in order to investigate stuff that is beyond the standard model, because it can give us a nice way to capture all possible effects. Now, in practice, what happens, this is a kind of a peek into the literature, is that there's actually a long chain of effective field theories that exist. I keep losing my, yes. So the big picture that people doing SMEFT nowadays have in mind typically is that you have some sort of energy spectrum from lowest to higher energy. Somewhere here in the clouds you have your UV that lives at a scale lambda. And this is the UV that is closest to us. There can be more UVs going up to string theory or whatever. When you hit the letter X scale, you have SMEFT. But then it has already been known for a while because people use these things for calculations. You can use other field theories if you go to lower and lower scales. For instance, there is one that is called weak effective theory or low energy effective theory that sits here, and I will tell you in a second what it is. You can go even farther to heavy quark effective theory, HQAT. You can go here to chiral perturbation theory and lower. You can even have other things to the side depending. So at some point, there are different limits that you can take depending on which process you're interested in. So as SMEFT we've seen, this wedge/left is the one that you might have seen if you ever heard of flavor physics. So this is the FT that you get from SMEFT, essentially subtracting out the top, the Higgs, the W, and the Z, and imposing only QCD plus QED. So if you, at some point, work at energies that are so low that you cannot produce the heavy bosons, so you are below the 50-something GV, everything that you have are the quarks, including the bottom or not. So typically the bottom is included. So say that you are at 10 GV, you have the bottom, and all the other fermions that are lighter, but you don't have anything of the heavy bosons. You only have gluons and photons. And so this is basically the modern take of Fermi theory. Okay, so what you have here is interactions mostly between fermions, so a lot of four-fermion interactions, plus things with photons and gluons, which don't do much because, gluons do, photons don't even interact with themselves, so you can only attach photon lines or do dipoles, for instance. There are many dipole operators. And this is used for flavor physics, so if you look into the B anomalies famously, this is an example that I used to make now, it's not, it doesn't sound as good, but the idea was really that when there was this B anomaly, so you had, it was a semi-leptonic decay, right? So you had an interaction between two quarks and two leptons. The analysis that led people to say, oh, it could be a leptoquark, was based on this kind of effective theory. So they had some 4-point interaction where they measured what this Wheatstone coefficient would have needed to be in order to have this sort of effect. And then they cross-checked it, so they turned it around and they said, okay, but if I look at the LHC and I produce two quarks that go to two leptons, I'm not seeing any resonance here, so it's not going to be something in this channel, it has to be something in the other channel. So the analysis is more sophisticated than that, of course, but it's kind of the sketch. So they kind of tried to resolve what would be in this effective interaction already. So they kind of tried to use already this machinery to do this work. HQAT is something that is used for hadronic physics. So this is a theory that takes the limit of where the bottom mass is very heavy, essentially. It's called heavy quark effective theory. So when you treat the bottom to be very heavy. And chiral perturbation theory, we just mentioned it, was historically introduced for pions. So pions are very light, right? So they're the same order as the muon mass. So this is a theory where you don't even resolve the quarks anymore. You just treat the pions as one composite state, and you can do pion scattering, pion decay, so two photons, and so on and so forth. So inside this great scheme of things, the plan is that you could essentially make each of these theories talk to each other. So the way you address this from a theoretical point of view is that here you hopefully want to have some renormalizable Lagrangian, some complete model, or maybe not, but say we write a complete model or a simplified model that has only dimension for interactions. Then here we do this operation of matching that I'm going to sketch for you in a minute. Matching means, no, we'll tell you later. So you match the two theory, imagine whatever you want for now. Then here you have to go from SMEFT down to the scale where you integrate out these bosons and the top. So here you will need to have some renormalization group running, actually, that I will mention on the very last day if I have time. I don't know if you will hear about it in the other courses for the other theory. But so SMEFT, because it has divergences, so you might know the standard model, the parameters of the QCD coupling, the two-way couplings, they run as an effect of the presence of infinities that have been renormalized, right? So they depend at the scale at which you renormalize them. SMEFT also has divergences at dimension 6, 8, 7, that are renormalized order by order. So if you have dimension 6 operators, there are counterterms of dimension 6 operators, and these parameters that are there, they run and they mix, which makes things very fun. So you go from one scale to another, you do that. Then here you do again a matching between this SMEFT and this other theory. Then you do another RG running. Down to this energy, you do a matching between these two, running, matching, running, matching, running, matching. And this is the consistent way of taking care of physics at very different scales. So at this point, you are at the MEV scale, and here you could be in the multi-TV, right? So there's a few orders of magnitude that run in between. And so the idea is that really you could use you could use this theory to kind of put everything together, let's say. So you could have measurements that are made at different scales. So for some measurements, it's more appropriate to use one of the other theories because, I don't know, if you're measuring like the mu on G minus 2, then it's not the same as measuring TT bar production. So it's a very different energy. So some theories are more appropriate than others, and we will discuss that on the last day as well. And then use all this machinery to connect up to the UV. And this is already automated, at least up to here. Okay, so there are codes that already do for you the matching running, at least up to the point where you can include flavor physics done in the weak effective theory or low energy effective theory. So let me just say the matching and then I'll let you go. So the concept of matching is that what you really want to impose is that your amplitude in the UV model or the FT that is above you is exactly the same as the amplitude calculated in the FT at some matching scale, mu match. So you choose an energy scale, and at that energy, you calculate the amplitude in the UV, you calculate the amplitude in the FT. You have already seen, even if you didn't realize, the example for the Fermi theory, so I'm going to repeat it. So when you're in the Fermi theory, your UV is the standard model, right? So where you have the W in there that is exchanged. And if you calculate the amplitude at 3 level in this case, it will have to be some minus I G squared, there is a 2 MW squared, and then there are the two fermion currents that are coupled there. Well, if you calculate it in the Fermi theory, you have a dot here, and your expression will be minus 4I GF divided by square root of 2 times the same two currents. So in this case, the scale doesn't really matter because we're calculating at 3 level, but you can do this at one loop, and then at one loop in general, this will depend on the scale explicitly. So you really impose that they are equal. And what this step does is that it tells you that as a consequence, G Fermi has to be 1 over square root of 2V squared. Okay, because so you get here, remembering that the mass of the W is GV divided by 2. You insert it in there, the G cancels out, and the factor of 2 also does what it has to do. And then you simplify all the numerical factors. So that is the formula that you should get, which, remember, is the 1 over 290. So this is why G Fermi is 1 over 290 and not 1 over 245, because there's square root of 2 in between. So basically, the matching operation, what it does is that it fixes, so it determines the formula, the expression of the Wilson coefficient as a function of the parameters of the model that stays above at a higher energy. So this is at 3 level. You can do it in one loop. You cannot, I mean, you can do it at 2 loops, but no one has ever done it. So up to 1 loop, this is kind of a solved problem. There are even automated codes that do it. So the method that we saw here is called the diagrammatic method. So in practice, you need to calculate every single possible amplitude in your theory, the 1pi irreducible. And you have to impose that they're exactly equal. So you have to calculate in the theory, calculate in the FT, and equate all of them and solve this giant system of equations. Or another method that is a bit more practical is to do it with functional methods. So what this does is that essentially you do this matching operation really at the level of the effective action that is the expression that, so from where the diagrams come from, right? So it's done at a bit more fundamental level. So I'm not going to explain this because it's really going a bit outside of the scope of the course. But if you want to do the functional matching at 3 level, is really trivial. And it consists in solving essentially the equation of motion for the heavy field, heavy particle. So from which you extract essentially the classical solution and then you replug it inside the Lagrangian. And I'm gonna sketch it hyper quickly for the Fermi theory. So for the Fermi theory, you want the equation of motion of the W, which looks something like box minus mw squared times eta mu nu minus the d mu d nu factor. You have, for instance, a W minus here, and this will be equal to G over square root of 2 L bar gamma nu, the projector L plus the terms with quarks. Let's say that we are doing only the muon decay. So this is the equation of motion of the W. You solve it, which means that you obtain something which is the classical solution of the W, which has to be this kinetic operator inverted times that part there. And then you expand in the power counting. So essentially you want to expand in powers of the momenta over mw. So you take the limit in which mw goes to infinity. And the first order is very easy because it's clearly only that term. So this essentially remains minus eta mu nu over mw squared, and then the fermion current, plus higher order interactions. So your classical solution of the W is really like an eta mu nu and the current and mw squared. So what happens is that this came from the standard model Lagrangian, so where you had interactions that were like this in the original Lagrangian, right? So you take the equation of motion, you solve it, you take the classical solution, and you stick it back in. So now we take this, and this becomes a minus, and then you have, this becomes a mu, basically squared, divided by mw squared. Okay, so you have one fermion current that came from the fact that you had the original interaction, and one fermion current that comes from here, from the solution of the equation of motion. And what you just obtained is a 4 Fermi interaction with 4 leptons that have the right chiralities and charge assignments and so on, and goes like 1 over mw squared. So if you do this, well, yeah, I forgot the G over square root of 2 and so on. So if you do it properly with all the numerical factors, you will get exactly this matching here. So you get exactly that if you solve the equation of motion, you will get this expression for the interaction. And then you can call whatever you have in front G Fermi, and you have done the matching. And there is a much more sophisticated technique to do this at one loop, which is where this functional stuff is really, really powerful because you don't want to calculate millions of loop diagrams. And it is already, so there are some codes you can find in the literature. I can give you some references in the files that I will upload. Some of them use the diagrammatic method, most of them use the functional method. And so you can virtually give them any new physics model that you want, and we'll spit out what the SMEFT Wilson coefficients look like, matched up to one loop in the two theory. I forgot to mention, but it's obvious from here that so this works if the new physics model is weakly interacting. If it's strongly interacting, you don't know what you're calculating, so this is not the way to go. There's no real way, there is no real procedure to do it, especially because when it's strongly interacting, sometimes you really change the degrees of freedom because you go to composite states, and so there's no perturbative physics in there that you don't know how to calculate, so it's not always possible to do this matching. But when both theories are weakly interacting, this is the idea. Okay, so I'm going to close it here, and tomorrow we will look a bit more into dimension 6 and start doing some pheno and some more heavy calculations. Almost.